So the first thing that we need to look at is how files are actually stored. Now clearly files are stored on the hard disk, but how are they arranged? Now the obvious answer to that question is, well, they're arranged into directories and subdirectories, which is conceptually true, but it's not technically true. So I'll begin by asking you the following question. What does it mean to say that a file is in a directory? Now if you think you know the answer to this question, I will throw into the pot the following fact. If you examined the data inside every file in a given directory, you would find that that data is scattered around the hard disk with no obvious connection. It is absolutely untrue to say that all the data in the files of a given directory are grouped together on the hard disk. So, let's look into this a little further. Firstly, it's very important to understand that everything on a Unix file system, if you don't know what a file system is, I'm really talking about a hard disk, is a file. Everything is a file. Even directories are files. That might sound like an odd thing to say. Surely files are files and directories are things that contain files. You might think of files as oranges and the directories being the boxes that you put the oranges in. But I assure you that a directory is also a file, albeit a very special and unusual type of file. So, if a directory is a file, what does it contain? What is in that file? Well, a Unix directory file, if you want to call it a file, simply contains a list of file names and inode numbers. I'll explain what an inode number is in a second, but I want to stress that that is all the information that you'll find in a given directory file, just a file name and an inode number, a mapping, if you like, between file names and inode numbers. Against every name you will find a single inode number. Or, put another way, against every inode number you'll find a single name. There is no other information in a Unix directory file. There's no information about file sizes or dates or permissions or anything. Just file names and inode numbers. Have a little look at a diagram of what that might look like. If you were to actually conceptualize a directory file, it might look like that, with a list of file names followed by a list of inode numbers. So now that we know that, let's find out what an inode number actually is, because they're obviously quite important. Well, you could say that an inode number is simply a reference to an inode in the inode table. That's not a particularly helpful definition of an inode number because we still don't know what an inode is, but now we have the idea that there's a whole table of these things and that each one has a given number. And that's exactly true. They're numbered from, say, 1 up to maybe several 100,000 or several million. There is a great number of these things in the inode table. Now, if you are familiar with DOS and or Windows and the way files are stored in DOS and Windows, they're stored in something called a FAT, F-A-T, file allocation table. Or in certain versions of Windows you might find this being called FAT32 or even VFAT or something like that. Anyway, what we call the FAT in DOS and Windows we call the inode table in Unix. If you don't know what a FAT is, don't worry, I'm about to explain it. So, we have a table of these inodes, and each individual inode, I is short for information, is the set of details about a single file on the disk. What details are we talking about? Well, we're talking about the file size, file creation, access and modification times, the file's owner and the file group, the file's permissions, the file type, whether it is a regular file or a directory file or a device file. If you don't know what those are, you will later on in this chapter. Its link count, again you'll learn about link counts later on in this chapter, and a block number, which again you'll learn about in a moment. This is the information you'll find in an inode. Each inode contains one of each of those things. And the inode table contains several 100,000 or several million inodes, and each inode is numbered. And it's those inode numbers that you find in a directory file. Notice that what you don't see in an inode is any reference to the file's name. The name is actually stored in the directory file. Nor, and this is very important, nor do you see any information about what is in the file. The actual data that's contained in the file is not stored in the inode. That is stored elsewhere. That's stored in a block, and we'll look at that in a minute. Now it is actually possible to display the inode number for each given file in a given directory, and you use the ls-i option to do that. I'm going to show you a diagram of all this in just a moment, so hopefully your concepts will get a little clearer. But in the meantime, I just quickly want to show you the use of the -i option with ls. Okay, here we are in the course folder again, ls-i, and now you can see the inode number listed to the left of each file name. And what you're looking at there is all of the information, every single bit of it that is stored in the directory file. Just to clarify your concept of what a directory file is, well, remember that the shorthand for the current directory is just dot, so I could do an ls-l of dot, but I'll also use the -d option, which lists the directory file itself rather than the contents of the directory. So ls-l -d dot, and I get the following. This is very similar to the listing of any regular file, except that I've got a D at the beginning. The very first letter on this output line is a D, indicating that it is a directory file. Notice that the file has a size. It's 512 bytes. Now you might think, well, what's in those 512 bytes? Well, I'll tell you what's in the 512 bytes. It's the list of file names and inode numbers that you can see above. That modification date that you can see there is the last time that that list of file names and inode numbers was actually modified. In other words, the last time I either added, deleted, or renamed a file. So you're getting the idea of what a directory file is now. You can see what's in a directory file, and you can also see the inode numbers. Let's now have a look at a diagram that shows the relationship between file names and inode numbers. So let's pull up our little diagram of the directory file again. There it is. And now let's pull up a little conceptual diagram of the inode table, which might look like that. I'm just showing 4 of the entries in the inode table, all consecutively numbered, 4573, 4574, 4575, and 4576. And remember that each one of those is an inode, and each one contains information about the file size, the owner, the group, the permissions, the block number, and a couple of other things. So what's the relationship between them? Well, you can say that any given inode reference in the directory file corresponds to one inode in the table. Now what that means is that the file name that has that particular inode, which would be in this case jjchap1.html, happens to be owned by Fred in the marketing group with a size of 966 bytes and a certain set of permissions with block number 91283. So when you do an ls-l, the program ls obviously goes and looks up that information in the inode table. Okay, now, but we still have not yet seen where the actual data that is contained within the file. We've got this file called jjchap1.html. It's clearly 966 bytes in size. Where is it? Well, let's have a look. You can think of the data being stored in blocks. Just like an inode table, there is a block table as well on the hard disk. In fact, the great majority of the hard disk is given over to storing blocks. The blocks are where the actual data contained within the file lives. And it's probably fair to say about 90% of any given hard disk is given over to blocks. The remaining 10%, or perhaps less, is given over to the inode table. Anyway, that you recall that the particular inode that we were looking at had a block number of 91283, which means, of course, has a reference, if you like, to that particular block number, which looks like this. So now we can see the complete chain. With the file name, we can get the inode number. Once we've looked up the inode, we can get the block number, and once we've looked up the block number, we can get the data in the file. So any time you want to examine or modify the data in the file, the computer goes through this process for you. So it's then fairly clear to see that the inodes that make up all the files in a given directory could have radically different inode numbers, which means, of course, that they could then have radically different block numbers. And that means, of course, that the data that is contained in the various files in that given directory could be scattered all over the hard disk. They're only gathered together, if you like, by the organization of the contents of the directory file. I hope that diagram serves to make all of this a little clearer.